As usual, let's start with the check from home that you can hear. Can you hear from home, anybody? Okay. I also share the screen, so for the virtual class, it should be all set. Okay. Now. Okay, so today we will resume talking about probabilities, and we start discussing density estimation in the context of classification. Before we start, are there questions on the things that we saw last week? So we revised probabilities and we started to introduce some distributions that we will need, the Bernoulli, multinomial, binomial, and categorical, and the Gaussian density. And then we extended that to multivariate version of the distribution. Are there questions? Okay, so where we stopped last week was with a problem that we will see again later, but it's easy enough because it's intuitive, the solution, so it's easy enough to start with this example to see how we can build a model that describes the probability of something that will happen, and then we will see how to use this for classification. But for the moment, we are doing density estimation. So we have a problem, predict whether a coin flip will result in a head or tail when we don't know the probability with which each of the two outcomes can appear, because the coin may be biased, so we don't know what is the probability. And we have access only to a set of previous observations. So somebody tosses the coin several times, and then we try to predict what will happen next. So our goal is to build a predictive distribution that describes the coin toss, the next coin toss xt, given the previous observed coin tosses. And we said for this we use as model probabilities, random variables. We describe each toss as a random variable that gives us outcome 1 when the toss gives head, and outcome 0 when the toss gives tail. Then we said if we knew the probability of a single toss giving head, then we can model all our coin tosses as independent, in the sense that if we know the probability of a single toss giving head, knowing the previous coin tosses is irrelevant, because that we assume that they are independent given the value for pi. And then we have seen that since this is a two-outcome problem with an outcome having probability pi, essentially the random variables are distributed as Bernoulli random variables with parameter pi. This is also true for the next toss. So if somebody tells us what is pi, then we can say what is the probability that the next coin is head. That's exactly pi. The problem is we don't know pi. So we need to figure out how to estimate a value for pi. We said we follow frequentist approach, so we assume that there is a hidden, unknown value that is responsible for the tosses, and if we knew this value, then we know everything we need to know about the single tosses. The problem is we don't know pi, so we need to estimate pi. A possible way, that is the way that we will follow, is some possibly intuitive approach. I hope it's intuitive. If we select a value of pi, so if we say that the probability of a head is pi, then for a given value of pi, we can compute what is the probability of the tosses that we observed. So for example, let's imagine that we observed somebody tossing 3 times head, tail, head. If we assume that pi is 0.5, this sequence has probability 1/2 to the power 3. If pi is 0.1, then we have 2 head and 1 tail, so the probability of this sequence is 0.009. The probability of the sequence depends on pi. So the probability that we obtain a sequence like the one that we observed is a function of pi. This function is also called likelihood function. It's a function of the parameter that corresponds to the probability of the observed values, my observation, the previous tosses, the previous coin tosses, the data that I'm using to estimate the model parameters on, the probability of those data if we assume that pi is the parameter of the model, of the Bernoulli distribution in this case. So it's a function of pi, and it's computed as, if pi is the parameter, that's the probability of the tosses when computed with that value of the parameter. So in this case, this would be a product of Bernoulli densities, since they are independent. Now, the idea here is a good value for pi can be what? Well, if we test many pi's, we will see that under some pi, the observation will have a higher probability. With other values of pi, the probability of the observed values is smaller. So the idea here is, if we need to select one value, let's select the value under which our observations are most likely. So the value which maximizes the probability of the observed sequence. I don't know pi, I have an observed sequence, I will select the pi for which the observed sequence has a higher chance of happening. So for example, in this case, if I select pi is equals 0.5, the probability of this sequence is 0.125. If I select pi equals 0.1, I get this probability. If I select pi equals 0.9, then I get 0.9 to the power 2, because I have 2 heads, and then 1 tail, which is 0.081. I can try to see all possible values of pi. I would end up, in this case, the optimal value we will see would be 2/3 for pi, because that's pi for which the probability of the sequence is the highest possible. Which means that our goal is to find what is called the maximum likelihood solution. Maximum likelihood estimate is the parameter pi that maximizes the likelihood function. So we have our likelihood function, and one possible way to find pi is to maximize this function with respect to pi. Now, how do we obtain the maximum likelihood solution? So the solution under which our observations are most probable. Well, we need to maximize this function. How can we express this function as a function of pi? Well, first of all, we said, given pi, the tosses are independent. If they are independent, I can factorize the probability as a product of probabilities of the single tosses. And for each random variable xi, the density is the density of a Bernoulli random variable, which we have seen we can express in this way when we introduce the Bernoulli. It's pi to the power xi, where xi is the observed value, times 1 minus power 1 minus xi. So for example, if I have head, tail, and head, here I will multiply by pi, because here xi will be equal to 1, xi will be equal to 0, xi will be equal to 1 again. So this will introduce a multiplication by pi, this 1 minus pi, and this by pi again. So overall, I get, well, the overall doesn't matter now, but each observation contributes with pi if I observed 1, and with 1 minus pi if I observed 0. This is just a compact way to expressing that. So the likelihood becomes a product of these terms over samples. Notice that again, for each sample, either one of these will be 1 and the other will be 0. So either xi is 1, then 1 minus xi is 0, or vice versa. So our goal is to find the maximizer of this function. Now, this function is a function of pi to some power, so it's not directly easy to work with this kind of expressions. We will see that this holds true also for other densities. So rather than working directly with the likelihood, we typically work with the logarithm of the likelihood. Remember that the likelihood function is a function for discrete random variable that contains probabilities. These probabilities are typically greater than 0, so we can are all positive, so the likelihood function is a positive function. So we can take its logarithm. We cannot have a likelihood function that takes value minus 1, because probabilities are always positive. So we can take the logarithm, and the logarithm is monotonically increasing, which means that the log function is strictly increasing as we increase its input, which means that the maximizer of L is equal to the maximizer of the logarithm of L. So we can maximize the logarithm of the likelihood that will give us also the maximum of the original likelihood. Well, the maximizer of the original likelihood. So we will find the same pi. Now, we see that we will work with logarithm of densities essentially through all the course. One reason is, within a moment, working with the logarithm of the likelihood gives us easier to manipulate expressions. Then we will see other reasons. One reason is that working with probabilities numerically will easily lead us to underfitting problems. We will discuss that in a laboratory, but consider already this case. My likelihood function is a function of p. Then we have seen that every time I have a toss head, I will multiply by pi, sorry, pi, not p. And when I have a head, I will multiply by one tail, I will multiply by 1 minus pi. So essentially my likelihood will be pi to the number of tails times 1 minus pi to the number of heads and number of tails. If these are all values smaller than 1, then what happens when I take these powers? This value will quickly go towards 0. Numerically, it means that if I have a large number of samples on a machine, this will become 0, which is not correct. It becomes 0 because of approximation errors in my floating point numbers. So we cannot compute this expression correctly with lots of samples. While we will see that with the logarithm we can do that, and we will see why in a moment for this likelihood. So this solves also numerical problems. Then we will see, when we talk about classification, that working with logarithm of probabilities will lead us to produce what is called a classifier score that will have some properties that if we were to express it in terms of probabilities, they will not hold, but we will see that later. So there are many reasons to work with logarithm. For the moment, one is that it simplifies expressions. Why? Let's take the logarithm of the function. We have the likelihood is a product over samples, our observations of these expressions. Now, if I take logarithm of this product becomes a sum over samples. So now, rather than multiplying over samples, I'm summing over my observations. In this side, what I have? Logarithm of this expression, I have a product. So it becomes a sum of two logarithms. The first is what? Logarithm of pi to the power xi. So it's pi, sorry, not I, xi to, it's xi logarithm of pi. And here I have, let me write this a bit further, 1 minus xi logarithm 1 minus pi. This is a function that we need to optimize in terms of pi. Now, this expression is easier to work with because we can take its derivative. We know how to take derivative of a logarithm. It's easier to work with respect to derivative of a power that then we need to set equal to 0 and so on. In this expression, to find the optimal, we set the derivatives equal to 0. And then we look for the solution. To be more precise, what we are trying to do is to find the maximizer of the log likelihood under the constraint that pi is between 0 and 1. So we should enforce the constraint that pi represents a probability. Now, in practice, we will see that the solution that we find ignoring the constraints will give us a solution that implicitly meets the constraint. So since the solution of the unconstrained problem is also a solution of the constrained problem, then that solution is the optimal for both problems. If I have something, find a value x that minimizes f, overall, if it also minimizes, well, okay, let's ignore this last part. If I have this function as a function of pi, and I need to minimize with respect to pi, subject to the fact that pi must be between 0 and 1, if I minimize the function without the constraint and I find that the global minimum is between 0 and 1, that is also a minimizer of the constraint problem. So we try to solve it without the constraint. We see that this does not always work. For other problems, we will need to enforce the constraint, otherwise we will not get the correct solution. But in this case, we simply set derivatives equal to 0. We solve for pi, and we obtain this expression. The solution for pi is 1 over n sum over I of xi. But remember that xi is 1 if I have head, 0 if I have tail. So what is the sum of xi? What is the sum of xi? If I have 1 every time I see a head and I have 0 every time I see a tail. It depends on the number of heads. If I have head, tail, head, how much is the sum of xi? If I have this sequence, this xi here is 1, xi is 0, xi is 1. So the sum of xi, of the xi's is 2. If I have head, tail, tail, how much is it? It's 3. So this is the number of heads in my observation, in my data set, where n is the total number of observations. So what we get is the intuitive solution. Pi, we take it to be the frequency of heads in our observation. It's 1 over n times a value that corresponds to the number of head tosses. Now this looks like an intuitive solution. And indeed, for many cases, it will be for us a reasonable solution. Now the frequencies word says that there is a true pi t, that if we knew it, then we can say that xt, that the probability that the next toss is head is pi t. And that's and that this does not depend on the previous observations. We still don't know pi t because we have only this estimate, but the frequencies approximation says, okay, let's make this let's approximate this by the pi that we found. So essentially, in the frequency toward our predictive distribution, the probability of xt being, in our case, head, given x1 to xn equal to something, should be pi t, but since we don't know pi t, we will approximate it with the estimate that we have of pi t. In this case, the maximum likelihood, if we use the maximum likelihood estimate. And in the approximation, once we know pi t, this will not depend on the previous samples anymore. This will condense all the knowledge that we can extract from the training set. So from the training set, we will extract the parameters, and then we will assume that those are the correct parameters so that we can predict the next toss using this directly, ignoring what happened in the past. So essentially, we start from our data set, we get the estimate of the model parameters, and this is the data set. This is the learning stage. We learn the model parameters from the data, then we can throw away the data, and from now on, we will work with the estimate of the model parameter that replaces the true value that was responsible for generating our samples that we don't and we can't know. Questions here? Okay, then problems with this solution. If we have lots of examples, then the pi that we estimate will typically be good for our task. But imagine that you came when the game was just started and you observed 3 head tosses. So you have only 3 observations, all of 3 of them are head. What would be the probability that the next toss is head according to the model that we just described? It would be 1. Why? Because we assume this to be the maximum likelihood estimate, but the maximum likelihood estimate is the number of heads divided the number of tosses. We have 3 heads, we have 3 tosses, probability that the next toss is head is 1, which also means that according to our model, the probability the next toss is tail is 0. Imagine we go to the extreme, we observe 1 toss that is head, then our model will say that it's always head. But when we have 1 toss, we will always have that it's either a head or either a tail. So if we apply this model after a single toss, we know for sure that the model will give us a wrong answer unless the game is so rigged that the coin really gives always the same answer. But it's difficult to say that in advance. If the coin was biased, in any case, the first toss would either be a head or a tail. And applying our model, we would conclude that the coin is totally biased in any case, even when it's not. The problem is that when we do the maximum likelihood estimate, we are essentially saying, as in the frequentist approach, there is 1 value, we're trying to estimate it, we have limited amount of samples, so our estimate will not be good, and then we fail at predicting what will happen next. When we have lots of samples, on the other hand, pi will become close to will convert to a good solution and will allow us to make the prediction. What is the problem is that if we have few possibilities, essentially we are neglecting what in the Bayesian world is called the uncertainty over the parameters pi. The parameter pi is an unknown quantity. The frequency is treated as an unknown value that we need to estimate. From the Bayesian point of view, since this is an unknown quantity, it should be described in terms of the mathematical concept that we use to represent unknowns. What do we use to represent something that is unknown? We describe it in terms of probabilities. We said at the beginning, we describe events that we cannot control, that we don't know in advance, in terms of probability. But the parameters of the model are themselves something that we don't know. So in the Bayesian world, we would represent them in terms of probabilities. Why? Because the frequentist approach says the maximum likelihood estimate, or any other estimate that I can compute from my training set, is the exact value that I need to use. From the Bayesian point of view, that's incorrect. The Bayesian point of view says it's true that the maximum likelihood we see is a good value, but there may be other different values for this probability that may still explain reasonably well my tosses that I cannot ignore. For example, if I have head, head, and head, then the maximum likelihood pi 1 gives a likelihood that is equal to 1. But if I select pi equal to 0.9, my likelihood becomes, make the computation, 0.72. So it's just 70% of the likelihood that if I use 1. So it's true that with a pi equals 0.9, there is lower chance that I observe head and head and head. But that's not negligible with respect to the same probability computed with parameter pi equal 1. With the maximum likelihood solution, I'm saying this is the only solution. I'm neglecting possible competing solutions that, even though they are less likely, they are not that far from the selected one, from the frequentist choice, to be actually negligible. And you observe that, for example, if I selected pi equals 0.9, they would still allow for tail observations. Now, the problem is how we concretize this. Well, in the terms of the Bayesian world, we would not specify a value for pi, but we would describe pi in terms of probability distribution. So we would say what is the probability that pi, which is the parameter of a probabilistic model itself, is 1. What is the probability that pi is 0.9? What is the probability that pi is 0.8? And so on. Now, we will not see this in detail, but essentially what the Bayesian world would do is treat pi as a random value that is associated to a random variable. So we have a random variable that describes the model parameter pi. This random variable, we need to specify what is called a prior distribution that describes what are the possible values for pi before we observe the actual data. For example, we may say that for us, all values between 0 and 1 have the same likelihood. So we could say that, for example, a priori, pi is uniform in the range 0, 1. So before we observe any data, we don't have any knowledge on pi, so we assume that all the values of pi have the same likelihood. I don't say probability because pi is a continuous random variable, so it's not a probability, but have the same chance to be the correct answer. Then, once we observe the data, using Bayes' rule, we can combine the likelihood function, this is the same likelihood function that we introduced before, and the prior information to compute what is called the posterior distribution for pi. So, for example, at the beginning, before we observe any toss, this is our distribution for pi, so we believe all the values of pi are correct, are possible. When we observe 3 heads, depending on the, well, we're not going to show it, but what happens is that we will revise our probability using the probability rules, and we would end up with something that will look similar to this. So that tells us that 1 is really the most likely solution, but I have a full distribution that describes other possible values for pi. And then, what do I use to make my inference? Probability that the next toss will be 1. Well, I use all possible models, each weighted by, let me write it. I will have all possible models that tell us, given a value of pi, what is the probability that the toss will be 1, and I will weight all these models by the posterior probability that is the correct value for the parameters. So essentially what I'm doing is, once I have updated my posterior probability over the parameters, so it was something like this, then I will consider all possible values in a continuous way, so it's an integral rather than a sum, but it's like if I were considering all possible values, computing for every value of the parameter what is the probability that the next toss is had, and then averaging this over all possible models, each weighted by the probability that that model, I use the word probability, it's not correct because it's continuous, but to understand, it's like as if it was weighted by the probability that that model was the correct model. So I have a full distribution that describes all possible models that I can have. This distribution is modified by the data that I have. As I collect data, I will change the distribution over the model parameters. When I need to make inference, I will take an average of my inference answer averaged over all possible values of the model parameters, each weighted by the corresponding, I said probability, it should be said more correctly, likelihood of the corresponding model parameter. And the update follows the bias rule in the sense that once I have specified the prior distribution, this likelihood function is the likelihood function that we have computed before. So this is a function of pi. To compute the posterior distribution, I just need to multiply the likelihood by the prior and then divide it by the marginal with respect to the parameter itself, which is obtained by taking whatever is on top of this numerator and integrating it with respect to pi. This is the joint probability of the observed values and the parameter of the model being pi. So this is a joint probability on top. Integrating with respect to pi, I get the marginal. So I marginalize and I remove. I get the marginal with respect to pi. So I get the marginal for the remaining parts. So once I define this function, once I define the likelihood, and the likelihood, we have defined it before because it's this function. It's this function where the only unknown is pi because the xi's are the tosses that we observed. This, the exponential of this multiplied by the prior gives me the joint. Then the integral of this with respect to pi is a number because the only variable here is pi. The xi are the values that are values, are number, are 1 or 0 depending on the toss that I have. And that gives me the expression for the posterior probability. Now the problem, the real problem is two problems. The first, how we choose the prior. Before I said, let's say that all the values are equally probable, but we can show that this may not be the optimal choice for the kind of problem that we are considering. So how do I select a prior that reflects, the prior should reflect my prior knowledge. How should I select a prior when I have no prior knowledge? And this is a problem on its own, which has some solutions, but again, there are discussion on which is the best solution. And then, for us, the main issue and why we will not see these models is that typically computing this expression is difficult because of this integral. So the integral at the denominator of this expression is difficult to compute. So writing an expression for the posterior distribution in a general case is something that is unfeasible. We can do it in very special cases, but solving the integrals that are involved here in the marginalization and here when I build the predicted distribution, so when I average the models over the possible models, these integrals may be intractable in practice. However, if we are able to build Bayesian models, when we have few observations, these models will typically behave better than the maximum likelihood solution, or other frequentist approaches in general, because they account for the fact that we are not sure on which is the correct value that we should use for the parameters of the model. Okay, questions? Okay, now, having said this, let's go back to our frequentist world. And let's now switch to continuous random variables. We have seen how to build a density model for a problem that can be modeled in terms of binary outcomes, so Bernoulli distribution. Now let's do a similar exercise, in this case, with a Gaussian distribution. Why? Because why we consider Gaussian distributions? That's because they are distributions that appear in several cases. You have seen that in several occasions, in several cases, you have probably seen that Gaussian distribution can be used to give a good model of some data. There are reasons why the Gaussian distribution appears naturally in a wide number of use cases. For us, another reason is that it's easy to work with. So even when the data are not well modeled with a Gaussian distribution, given that the models are much simpler than using other distributions, it's still worth trying if the distribution, the Gaussian model, is good enough for our task, even when we know that it's not the best choice, because compared to other models, it's much easier to work with. We see that it has closed form expression for all the things that we need, while if we make the model even just slightly more complex, then we start losing these properties. We will see at the end of the course a second model that uses a slightly more complex distribution that is based on the Gaussian model, and we will see that training that model alone will require one class to explain why we train it in that way. So, for practical reasons, and because typically these are good approximations of phenomena, studying Gaussian distribution is a good point to start our analysis of continuous densities. So again, in this moment, for the moment, we concentrate on a density estimation problem. So we have some data set that we decided we model as a Gaussian distribution. For example, we may have drawn the histogram. We may have seen that the histogram looks like having a sort of bell-like shape. So we decided that we can model this data as Gaussian distributed data. Of course, every model that we use is just a decision we make, because the data is the data, the model is the model. The model is always wrong because it's not the reality. It's always a model of the reality. Whether the model is good or not depends on our goal. But let's say that we decided that we want to use a Gaussian model, then let's see how we can estimate good Gaussian model for the data. We have, again, for the moment, we restrict ourselves to one-dimensional samples. So, for example, we will see later that this may be the height of some people. So we measure the height of people in, let's say, Italy. We have the histogram of heights. And then we want to model this by a Gaussian density. Then we will ask ourselves if this is a good model later. But let's imagine we observe a histogram-like shape. Now we want to model these values as histograms, as Gaussian density. So we have our dataset that consists of the heights, and we say this will be modeled as random variables that are Gaussian distributed. Again, we assume that there is a Gaussian distribution with parameter mu and variance v, or if you prefer, actually, we will prefer to parameterize this in terms of the precision, that is the inverse of the variance lambda. There is the frequentist word, there is a distribution, a Gaussian distribution with parameters mu t, to be precise, mu t and vt, the real distribution parameters, this was responsible for generating the height of the people. Again, this is a model, so it's not true. The height are not generated by random sampling, but the model assumes this. So we model each sample as the samples as a set of independent, again, given the model parameters lambda, and identically distributed random variables xi. Given the model parameters, we say that the distribution of one of these random variables can be described by a Gaussian density. So the Gaussian density is the density associated to each of the samples that we observed. Now we can compute the likelihood as in the discrete case. In this case, since we have continuous random variable, we cannot say what is the probability that the height is 175, because since this is continuous, the probability will be 0. But we can ask us what is the likelihood, so the value of the density. That means, like if I was asking for the probability that I get a height that is in a very small range around value 175, so in a dx slice. As for discrete random variable, we can compute the likelihood, and in this case we define the likelihood as the value of the densities. Again, the likelihood is the value of the densities for the observed random variable given the model parameters. Now, these are not probabilities anymore. For discrete random variable, density and probability are the same thing. They are the same quantity. The probability density is a probability distribution density. Corresponds to the probability mass function for discrete random variables. For continuous, it's not. But in any case, we can define the likelihood in terms of the density. Again, we can imagine that the higher the density, the more likely the corresponding value. So if this is, for example, 175 and this is 160, it means that there is a higher chance to observe somebody who is tall 175 plus or minus the x, something like that, rather than observing somebody who is 160 tall. To be more precise, there is a higher chance that we observe the value 175 with respect to the value 160. So the density measures this. And we can define the likelihood as the function, the density for all the observed values. The joint density. Now, the joint density, again, since we have given the model parameters, the random variables are independent, can be again expressed as a product over the samples of the density for the corresponding sample. So each sample will contribute with its own corresponding density computed over the model. This is the Gaussian density, this fx, or without the I, since they are all distributed as random variable x. So I can omit the I because they all have the same distribution, is a product of Gaussian densities computed, for the moment let's write v, at xi. So if I give you a Gaussian distribution with mu and v, I can take my data set and compute the Gaussian density for these values, which may be, I don't know, for this Gaussian will be, let's say this is 160, 170, 75 and 180, these will be the values with this Gaussian. If I have a different shape for the density, then the value of the density will be different. If I have yet a different model, a different value for mu and v, the value of the density will differ. So the product of these values corresponds to the likelihood of the parameters, which measures what? Essentially, you can see that the higher the value of the density, the higher you can imagine the chance that these values were really created by the corresponding Gaussian density. With the blue density, there is a higher chance of observing these values than with the red. And with the red, there is a higher chance to observe these values than if we had them generated by the green density. For the green density, the likelihood of those values is lower. So the likelihood, in this sense, can be interpreted as a measure of, this is why the name, of how likely it is that we observe those values if the parameters of the model that generated them are mu and v. Higher the likelihood, the higher the chance that we observe these values if we sample from a distribution with the corresponding parameters. That's the same as the Bernoulli example before. The higher the likelihood, the higher the chance of our observation given the model parameters that we are assuming. And this is a function of the model parameter. As we change the model parameters, the likelihood will change. So we may have Gaussian distributions for which the likelihood is very small. For example, if I have mean here and this variance, the chance to observe these three values will be very small because these three values have a very, very low value for the density. It's very unlikely that if I sample from the yellow density, I will get 175, 180, and 160. If I sample from the blue one, there is a good chance that I can observe those values in my dataset. Actually, the probability is still 0 for the single value, but let's say the probability that I observe something in a small range around these values is much higher than with respect to the yellow density. So, in this case, the blue model can better explain the values that I actually observed in my dataset. Maximum likelihood solution will do exactly the same thing. We'll look for the values mu and v that maximize the likelihood function. Now, before we get to that solution, let's open a parenthesis and say that the maximum likelihood solution is not the only way to estimate the model parameters. That is, in the frequentist approach, our goal is to find an approximation that is called an estimator of the true value of an unknown density that was responsible for generating my samples. We're seeing that essentially this means that we start from our data and we compute. For the Bernoulli problem, it was the parameter that we said was estimated by maximum likelihood. For the Gaussian, we will see that we will find the optimal mu and v. But in general, the maximum likelihood is not the only way to estimate the model parameters. Any function that, given the data, gives us a value for the model parameters, this for the previous example, mu and v for the Gaussian example, is called an estimator of the model parameters. So an estimator is a function or a procedure, if you want, that given the data, gives us values that we will use as if they were the true value of the model distribution in the frequentist world. This function t, well, the maximum likelihood procedure is a function t. It's defined as the arc max over theta of the likelihood function, which is a likelihood of the parameters, and implicitly, we didn't write it, but it's a function of the data as well. So it's a function that, given the data, will return me parameters. This is not the only one. There are several others, but we will not see them. We will mainly restrict to the maximum likelihood, just to open a parenthesis, we say that this is not the only one. Typically, what we want are estimators that are consistent. That is, as the data set becomes larger and larger, so as the number of samples goes to infinite, they should converge to the true distribution parameter theta t. What does it mean? It means that if the data were really generated by a distribution with parameters theta t, then our estimator should converge to this theta t. Now, in practice, our data is never generated by distribution, so consistency only measures a theoretical property of a procedure that estimates data. It doesn't tell us anything about how good it will be for our data, but to ask that if we were really generating, for example, the samples from a Gaussian with mean mu t and vt, then our estimates would converge to mu t and vt as the number of samples goes to infinite. That is something that we ask because we would at least, that if the assumption of the models were true, we would at least recover the correct solution. The assumptions are never true, but that's another history. Now, the maximum likelihood estimation is a consistent estimator. So we can show that if the frequentist assumptions were correct, so if I were generating my samples really from a Gaussian distribution, then the maximum likelihood solution, as the number of samples goes to infinite, will recover exactly, will converge to the value or the true value of the distribution. There are other estimators that are consistent, that are sometimes used because they are easy to use. For example, another that I will discuss now that is fairly easy to adopt is the method of moments. The method of moments is again a consistent estimator that in general will require a larger amount of samples to give us a good solution, but in the infinite case, it will also converge to the true solution. That is typically used as initial step for complex algorithms because it's easy to implement. The method of moments does the estimate how? Well, let's see for the Gaussian distribution. The Gaussian distribution has two parameters. So we can compute the parameter mu and the parameter v, which are the mean and the variance, and we'll see why is that in a moment. But from these parameters, we can compute the expectation of the random variable, which is mu, and the expectation of, or centered moment, if you want, second centered moment, which is exactly v. Then we can do the same on our training set. So we can compute the expected, the empirical mean of the dataset and the empirical variance of the dataset. This is the empirical mean, so the mean computed over the samples. This is the variance computed over the samples. This is the mean of a random variable which has a Gaussian distribution with mean mu, and this is the variance of a random variable which has at its density normal of mu v. Then the method of moments says, let's match the moments, as many as we need to estimate all the parameters, and then this will give us a set of equations, in this case very simple because I have already here mu and on this side v, and from this set of equations we can find estimates for the model parameters. So we match the moments of the distribution with the corresponding empirical moments computed on the data. This will give us equations in terms of the distribution parameters, and this will give us a solution that tells us what are the estimates that we will use for the model parameters. Now, for the Gaussian distribution, this is straightforward because the first moment is exactly mu and the second center moment is exactly v. Now, this is not always the case. For other distributions that are more complex, the expectation of x may be a function of the parameters and so on. For example, we have seen was the Bernoulli? We've seen that for Bernoulli, the variance has this expression. So we could apply it to the Bernoulli distribution as well. We will compute the empirical variance of the data, and we will equate it to the variance of the distribution, and then solve for P. Actually, we will not do it for the Bernoulli, because for the Bernoulli, we would go directly through the mean, which is easy. But this to say, sometimes the expression is not that straightforward. It's not a function of directly one parameter of the model. So in some cases, the expression may be more complex. So it will give us a sequence of equations, a set of equations that we can solve. And once we solve those equations, this will give us solutions for the model parameters. For the Gaussian density, we said it's straightforward because the first and second order moments are exactly the parameters of the Gaussian density itself. So we can directly solve and obtain that the method of moment estimate is the empirical mean. And for the variance, here I would actually write like this, the empirical mean, not, which is the same because this is the same value, but I would prefer to write it in this way, the empirical variance of the data. Now, the problem with the method of moment typically does not produce very accurate estimator. What does it mean? It means that to converge, as in this case, to good solution, it requires lots of data. To be honest, I'm not sure that it always gives consistent estimate, that it's always consistent, because this I don't remember, and I don't use because typically you don't use the method of moments on its own in any case. So I'm not even sure that it would be consistent for every use cases. But for the Gaussian model, it's a good model. And for other approaches where we can use better estimators, typically these better estimators are not always available in closed form, so they require, to find better estimators, we need to define iterative procedures. In those cases, the method of moment may be used as initialization for iterative procedures that will lead us to better estimates. But now let's go back to our Gaussian model, and let's go back to the maximum likelihood solution. The maximum likelihood solution is the estimator is the estimator that maximizes the likelihood function that we have said is consistent. Now, we can find the maximum likelihood estimator by optimizing the likelihood function. So again, we need to take our likelihood function, maximize it with respect to theta. As before, it's useful to work with the logarithm of the likelihood and maximize the logarithm of the likelihood. As we said, this is the likelihood is the joint density given the model parameters of the observed values. So for our training data set. IID assumption, we factorize over the single random variables, each representing one sample. This is the independent, and this is the identically distributed. Here we lose the index I because they are all distributed as a random variable X that is Gaussian distribution. Taking the logarithm, again, this product becomes a sum over samples. And here I have the logarithm of the density for X computed at value Xi. This density is the Gaussian density because X is Gaussian distributed. So I will have here the Xi, the density of a Gaussian distribution of a Gaussian, I will have the logarithm of a Gaussian density with mean mu and variance v computed at each sample. This is a function of mu and v, and from now on it will be a function of mu and lambda. So if I give you a value set for the model parameters, then you can plug the dataset samples and compute the value of the likelihood for those parameters mu and v. That is, I have my samples, I give you a Gaussian model, you can compute the corresponding likelihood. I give you another Gaussian, you can compute the corresponding likelihood. We are actually computing the logarithm of this using all samples. For each model, I will get a different value of the likelihood, and I want to find the maximum. Now, to find the maximum, we need to plug here the expression for the logarithm of the Gaussian density. The only parameters unknown here are mu and lambda, which are the ones that we want to optimize with respect to. The xi's are all known. Now, what is the logarithm of the Gaussian density? And I don't know why here it's missing all the i's. The logarithm of a Gaussian density, we need to remember what is the Gaussian density, 1 over square root of 2 pi sigma square, but let's write it with the variance. So 2 pi v inside the square root, exponential of minus 1/2 x minus mu squared divided v. This is the density. Now, this is, let's write it like this, square root of v. Square root of v, we bring it as upside, and it's square root of lambda. Lambda is the inverse of v. So this is the square root of lambda is 1 over square root of v. Then we take logarithm. We have a constant that we don't care about, we'll see. Then we have logarithm of square root of lambda, 1/2 logarithm of lambda, logarithm of an exponential. The exponential is exponential of minus 1/2. Lambda is the inverse of v, so I can write it in terms of lambda in this way. So this is the expression of the logarithm of the density. Now, typically, here our goal is to optimize with respect to lambda and mu. So all terms that do not depend on lambda and mu are irrelevant for our problem. So we will collect them in constants that we will not write, because what's the value of those constants is irrelevant once. Well, what do we want to do? We want to find a maximum of a sum of these functions with respect to lambda and mu. So the terms that do not, additive terms that do not depend on lambda and mu, will shift our objective function, but the maximum will always be in the same position. So we don't care what is the real value of these constants. We can now write the log likelihood by putting this expression in place of the logarithm of the Gaussian. Again, all the constants are collected here. We end up with this sum. This sum we can expand the square, and we obtain this expression. We have a sum of terms. All these terms depend on the model parameters, and some constant that collects everything that we don't care about because they do not depend on lambda and mu. Now, well, let's say this. Okay. How we find the optimum? Again, we take derivative with respect to lambda and mu. We should ask that lambda is positive. We won't, because we will find a correct solution in any case. So again, we solve the unconstrained problem, and we will see that that's also the solution of the constrained problem. Remember that our maximization should require that lambda, since it's the inverse of the variance, is positive, because we need the variance to be a positive value. Derivative of the likelihood, I'm not going to prove it, but this is the derivative. Solving for mu will give the solution that is, again, the maximum, the same as the method of moments. It's the empirical mean of the dataset. The empirical mean of the dataset is the maximum likelihood solution for the estimation of the mean parameter. Then, if we look at the variance, well, we solve for lambda. Solving for lambda will give us a solution for lambda, and the solution will tell us that lambda to the power minus 1 should be equal to this expression. But lambda to the power minus 1 is the variance. So what we'll get is a solution for the variance, which is the empirical variance of the data. Solving for lambda just means taking the derivative with respect to lambda. I have the lambda minus 1 that comes from this term, and all these are linear functions of lambda, so what remains is just the constants. Or if you prefer this term here. Now, in this case, but only in this case, well, not only in this case, but in this case, but this is not general, the solution, the maximum likelihood solution and the method of moment solution are the same. So in this case, the two solutions are coincident. And this is why we use the 1 over n solution for the variance, because that's the maximum likelihood solution and we stick to the maximum likelihood estimates for this course. You may have seen in other courses or somewhere else that for the variance, you were suggested to use 1 over n minus 1 as estimate for the variance of a distribution, of a Gaussian distribution. Why? Well, because this estimator is an estimator that has some properties that I will not discuss in this course that make it a bit more appealing when you have fewer data. Notice that if you have lots of data, these two will converge to the same value. But since we already know that if you have few data, then using the frequentist approach is not the correct thing to do in any case, and I won't introduce this kind of machineries because in my opinion, this is not the things that you should do when you have few data. You should look for better ways to take into account the uncertainty rather than trying to get better estimates that are not correct in any case. So I will not open the parentheses on how to find estimates that have better properties for low amounts of data. For us, we will stick to maximum likelihood estimate, and in any case, there are better estimates that you can build that are something in between a Bayesian model and a frequentist model, that again is something that we will not directly see, that will be able to give you solutions that justify also in the Bayesian work the maximum likelihood as an approximation of a specific model. Particularly, the maximum likelihood model is the solution that we would use in a Bayesian world if we want to condense all the posterior distribution in a single point with a prior probability that is uniform over all the possible values. But again, this is something that we will not see. So for us, we will restrict to this expression because that's the maximum likelihood solution, that's the estimator that we will use. Once we have computed the maximum likelihood solution, our predicted distribution becomes the Gaussian density where we plug in the estimate values that we have computed. This summarizes the training set. So the training set is summarized by these values. And we use this as if they were the true solution. And then once we know this, xt is distributed as a Gaussian, so we will use this as if they were the true values, so that the density for a new sample can be described by a Gaussian distribution with these values. So the new sample is described by a Gaussian distribution with these values, and then we can compute its density, that is the Gaussian density, computed at the value xt that we want to predict what is the likelihood of that value appearing. So the height of the next person that I didn't see will be modeled by a Gaussian density with the mean and the variance computed from the training set. Questions? Okay, let's make break here. 10 minutes break. Okay, now that we have seen how to estimate densities, let's see how we can use these densities for classification tasks. So our goal now is to build a classification model. We start with a binary example, but in general, well, the example will be binary, but then we will describe the procedure for a generic K-class problem. As I was saying, for a generic K-class problem, so we have classes, we have samples, we have a training set, we will see, that is divided into K classes, and we will have samples of each class. And then our goal is, given a new sample xt, try to understand to which class it belongs to. Now, we will use a probabilistic model. In the probabilistic model, what is unknown? Well, for sure, the class is unknown, so we will represent the classes in terms of probabilities. We will model the class as probabilities. Then we will see that it's useful also to model the samples as random variables. This is the same that we did for the binary task that described the coin tosses. The coin tosses were described as binary observations. So we will use random variable to describe a sample. The next sample will be described as xt, the test. And for xt, we want to compute the class label ct. We use t to identify that it is the test sample, that is the sample for which we don't know the class for which we want to make inference. And then we will describe also the samples of the dataset with similar random variables. Now, we will prove this later under some assumptions, but it's, I hope, intuitive that if we want to classify a sample as belonging to a class, then if we have a model that predicts the probability of the class given the sample, then it's reasonable to take as class for the sample the one that has maximum probability. Why? Imagine you have a problem where you have pictures of cats and pictures of dogs. You want to predict the class as cat and dog. If I tell you, so you have an image xt, if I tell you that the probability of cat given the image is 0.8 and the probability of dog given the image is 0.2, if you have to choose a label, which one will you choose? Which one will you choose? Cat. Then we will prove that under some additional things, the best answer will be dog, but that we will prove that it's dog later. But for the moment, we say it's cat. Why? Because everything else being equal, then there is a higher chance that we are correct if we predict cat. And I said everything else being equal because we will say that if other things are not equal, then this is not the optimal answer anymore. But again, this is something we will see around Easter time. So for the moment, it makes sense to say the image is the image of a cat. So if we are able to build a model that gives for all the possible classes what is the probability that that class is the class of the sample, so the probability of the class given the information we know about the sample, so given the image that we have, that we are classifying, then we can use that model to compute the label of the sample. By doing what? Again, a maximization of the probability with respect this time to the class. So if we have a model that allows us, given an image, to compute the probability of cat and dog given the image, then we simply run a max over all labels and select the label that gives us the highest probability. This is called posterior probability because it's the probability of the class once we have observed the picture, the test sample. Here you have a binary example that we will use through the class. The circle points are our training set, the diamond is the test set. The answer of the problem, the question of our problem is, what is the class of the green sample? And we will try to answer by computing the probability of, in this case, red, given the coordinates of this sample. Let's call this sample xt, and the probability of blue given xt. And then we will use this information to decide whether that point should be labeled as blue or red. Another example, univariate, and we see a univariate example to give a real use case that is hopefully easy to understand. Before we saw the problem of building an estimate of a model for the height of a population, now we see a similar task where we have some forensic task, so somebody who's making investigations who wants to know what is the gender of a suspect. He only knows the height, but he wants to know whether it's more likely that the suspect is male or the suspect is female. We simplify and we use male and female. If you want, you can make it more classes by adding as many genders as you like. But for us, we will use this as a binary problem. Now, we have said that if you look at the population, you can plot the histogram of the heights. Typically, if you plot the histogram of the heights, you will see that there are two modes. These typically correspond to the two genders of the population. We can do better. We take our dataset, we build the histogram for male and for female, and we end up with something that looks like this. Now, depending on the place you run these histograms, they will look different. So this can also be used to distinguish people from, for example, north countries and south countries. Typically, they are taller in the north. So, but in any case, you can see that there are differences in the distribution of these two classes. If I tell you the suspect is 150 from these histograms, which is here, what would you be led to say about the suspect? Is it more likely to be female or male? You would say female because there is a high chance to see 150 in the female class than in the male class. If I say it's 180 or 185, so we are in the middle, 182 in the middle of this bin, then there is a higher chance to see 182 in this bin. Now, you answer female, but this is not the whole story. We will see that in a moment. In any case, the idea here is we can build a model that describes the relationship between features and classes by building a joint model that describes the distribution of samples and corresponding classes. So for each sample, we actually have a feature vector xt. For the sample t, we have a feature vector xt and a class ct, or in general, if it's in our dataset, it will be xi, ci. We want to build a joint density for these two random variables that describe the class and the height. So what is the joint distribution of the class and height? So for example, this will answer us what is the likelihood of having somebody who is 175 tall and male, or 175 tall and female. Now, why do we do this? Well, because if we have this model, and then we will see how to build this model, once we've built this model, that's all we need to answer to our question. Our question is, my suspect is 175. What is the probability that is male? What is the probability that is female? And of course, this sum up to 1. So once I know one, I know also the other. So if I can compute one of these, then I can compute all of them, because for any problem, if I have k classes, once I know the solution to the probability of k minus 1 classes, the other one is known if it's a closed set problem. Here is a closed problem, so once we compute one, we know both, and in any case, once we know both, we can select which is the maximum and answer to our question whether we should label it or her as male or female. But once I have the joint distribution, then I can compute the class posterior probability. I have everything that I need to compute class posterior probability. Why? Well, again, what do I know is the sample is 175 centimeter or whatever, the height of the suspect. Probability of male given 175 is the joint density for 175 and male divided by what? Bias rule, the density computed out 175 of the height random variable. This one, if I have the joint model, I know it, because if I have a model that gives me this quantity, this is exactly what I need to compute at the numerator. So we'll see how to build this model. But for the moment, imagine that I give you a function that says that, for example, well, this is a normal computed at xt with mean 180 and variance, let's say 900. I'm making up numbers. This is a Gaussian density that depends on the sample. Here I plug in 175. I plug this in the Gaussian density expression. Everything is specified. I plug numbers. I run it through my machine, which computes the answer. It will be exponential of minus 1/2 175 minus 180 to the square divided by minus 100 times whatever is at the constant in front. So this is a number, if I give you the model for this. The denominator is easy. If I give you a model for this that works for all classes, then to compute the solution for the female class, I need to compute this expression. Now, how do I compute this? This is the marginal of the joint with respect to the class. So since I have only two classes, this is obtained by marginalizing the joint density with respect to the class variable. That means, since the class variable is discrete, it's a sum over all possible values for the discrete random variable, so for the class label, of the joint density. This is exactly the marginal. In any case, I want you to observe that since this quantity is the same in both cases, even if I don't compute it, I can already answer which one is higher between these two. Because since the denominator of those two fractions is the same, it's the numerator that decides everything. So the joint already tells me which is the class label that I should assign. But I can compute the marginal. Notice that to compute the posterior, I need to know all the joints. To compute the marginal, once I know all the joints, it's just a matter of summing the numerator of these fractions. So if I have this model, I have the solution to my problem. I can compute for every class the probability of the class given the sample, and then I can compute which is the maximum one. So the question is how we can build a model for the joint density. So what we need to do is now to define what is a good model for the joint density that I can use to describe my features. Now, this is where the difference lies essentially between generative and discriminative models. In generative models, we will factorize the density in this way. Remember that the joint density between class and labels can be factorized in two ways. Can be factorized as a class conditional density times a marginal for the class, or can be factorized, and we will see these are discriminative models, as a class posterior density times a marginal for the feature vector. This, we will see later, leads to discriminative probabilistic models. This leads to generative models. Because in generative models, because in discriminative models, what is the difference? In discriminative models, we will see that we will not actually build this joint distribution because what we are interested in is directly the class posterior distribution. So in the discriminative models, we will see that this term will not be actually modeled. So the joint model gives us more the generative model gives us more information because it describes the joint, while we will see that in the discriminative model, we do not need to specify the whole model. But we will see that when we see discriminative models. For the moment, let's just say that we have these two ways of factorizing the joint. In the generative model, we use this factorization. We factorize the joint distribution as what is called class conditional density and a prior probability. We'll make this a parametric density that we will learn, and we will discuss in a moment what's the role of this second term. So essentially, in our generative model, we will represent the joint density as a product of a class conditional that is parametric. So we will learn the class conditional density times a prior class probability. Questions up to here? Okay, now let's open a parenthesis that will stay with us for a long time. And that is something that is actually one of the things that I think gives you most problem at this point, not most problem overall, but most problem at this point, is the role of the class prior probability. Now, the class prior probability represents what? Well, in generative model, typically the class prior probability represents some information that we have on our task that is not directly related to the model that we make for our features. What is a prior probability? The prior probability is the probability of observing a sample of a class without actually looking at a feature vector. Let's say that I take a picture and I want to label it as a cat or a dog, but I don't look at the picture. So how can I answer? Well, for example, if you know that I like cats, then you can say that without even looking at the picture, there is 90% probability that I'm taking picture of cats, because usually I don't take picture of dogs. I like cats, so most of the pictures I take are of cats. So without looking at my picture, you can already express some belief that the picture will be a picture of a cat. This is the role of prior probability. Represents the probability that we expect the sample, the probability with which we expect a sample belongs to a class before actually observe the sample itself. So if I were to take one of my pictures at random, probably with a 90% probability, it will be a picture of a cat. Then once I look at the image, I may end up concluding that it was actually a picture of a dog. We'll see how this process leads to changing our opinion with the example. But the prior probability represents information that I have before I apply my model. And in this sense, it's typically not directly related to the model itself. If we follow a frequentist approach, we can think of the prior as the frequency of cat pictures among the data that we will have to classify. Notice that this is not the data in our training set, it's the data that we want to classify. So we can assume that if we want to classify pictures, if we say the probability of a cat is 90%, we believe that when if we collect many of the pictures that we want to classify, 90%, about 90% of those will be pictures of cat. So if I take randomly one picture, there is a 90% probability that it's a picture of a cat. Now, where the problem comes from? Well, first of all, we call this application prior because it's knowledge that is task specific. And typically, this is not something that we want to embed in our classifier. We want our classifier to work well regardless of the prior probability of the pictures being a cat. Imagine you have a classifier that predicts what is the picture, whether it's a picture of cat or dog. We want it to work well for me who likes cat. We want it to work well for somebody who likes dogs. So in this case, the prior probability of cat will be 0.1 maybe. So our model should not rely on, well, should be as much as independent as possible with respect to the application prior probability. Why? First of all, because we may want to deploy our model in very different scenarios where the prior probability are different. And we typically don't want to retrain our model for every specific use case. But ideally, if we have a model that works well, regardless of the prior probability, and can take data into account correctly, but doesn't need retraining every time we change the prior probability, that's a plus. So, for us, this is something that is related to the task that we want to solve. Typically, that means that whoever uses the classifier will plug in the prior probabilities, but as much as possible, we want this step to be separate from the learning stage where we learn the model of the data. So where we learn this part of the model. Now, in some occasions, we may be asked to also figure out what are good prior probabilities for a specific task, because the committer, whoever buys our product, says, I don't know, but I know that this data reflects the prior probability of the class. Then in that case, I can try to estimate as well from the training set. But typically, we take this as a specification that is given, and we want our model to be independent of that, or to be able to adapt to different priors if we change our prior specification. Now, as I said, the main issue is that the application prior depends on the use case, and it's not necessarily the frequency of the classes in the training set. As I said before, imagine that I have to use the same recognizer for me who likes cats, so 90% prior probability of cat, and somebody who likes dogs, 10% prior probability of cats. The model is trained on some data, which probably will have around half of the pictures of cats and half of the picture of dogs. The empirical prior for the training set is 1/2 for cat. But this is neither the prior for my application, cat prior equal to 0.9, nor is the prior of somebody who likes dogs. Prior for cat equals 0.1. So the application prior may differ from the training set prior. It may differ because we want to apply the same classifier to several different problems, and we cannot afford to retrain a specific model for each use case, so we want it to be application independent. It may even be that we know already what is the prior for the application that we want to simulate, but we are not able to create a training set with the same empirical prior. We said that we want our training set to be as close as possible to the evaluation set, so the question may be, shouldn't it have the same empirical prior as the application prior? Well, the answer is, typically we can't. One case, we have lots and lots of applications. We can't afford to have a training set that has different proportions of the samples for every application where we want to deploy the model on. Or we have a single application in mind, so we're training a model for a specific application, but that application is, for example, very unbalanced, and that was required to build training set that, if they were to have the empirical prior equal to the application prior, they would become untreatable. For example, imagine that I am much more cat lower than I said before, so probability of a cat is 0.999, probability of dog is 0.001. What does it mean? To create an empirical training set which has the same probabilities as empirical prior. It means that every one picture of dog, I need to have 999 pictures of cat. If I want to have 1,000 pictures of dogs to build a robust model for the dog class, I need my training set to include almost 1 million of pictures of cats. Probably these 1 million are much more than what I need to create a robust model for the cats. They are there just to simulate the empirical prior. Probably I can build good models with pictures of dogs and cats that are similar, and then if I can build good models that can adapt to different prior probabilities, I don't need to have the training set which has the same empirical prior as my application. So here we have at least two priors. We have the application prior, which may change from application to application. We have the training set empirical prior. And then we see we have the evaluation and validation set empirical priors, which themselves may be even different. So each data set will have its own prior. We want our models to be as independent of the prior as possible, so that then we can change the prior as we need, and things will still work nicely. So for us, we will assume that the prior probability is given, and we'll try to create our models in such a way that they are not influenced by the value of this prior probability as much as possible. We see that it's not always possible. With generative models, we can. Why? Because with this factorization, you see that I can factorize the problem into two components, where the first component I can make a model for, and the second component is exactly the thing that I want to keep separate. So I can create a model for the class condition, and then once I have this model that is built without caring about the prior, I can plug the prior probability for the specific application that I want to solve, and use the plugged-in value to compute class posterior probability. So my model will focus on this term alone. This gives me a model that is prior independent, in the sense that it does not depend on the specific prior that I want to apply my model for. Of course, when I want to perform inference, I will need to combine the class conditional model, that is the model that we will build now, with the prior probability to compute the joint density, and then from the joint density I can compute class posterior probabilities. Questions? Okay. Now, so our goal now is building the class conditional density model. The class conditional density model describes what is the distribution of the features inside each class. We have a continuous problem because we are focusing on the height estimation problem, so our feature vectors are continuous. We need to create a density model for our data. What is a good model? Well, the answer is it depends. I need to have more information on the specific task. For our task, we can observe that probably a Gaussian-like density will provide a good description of my data. So I may decide that it makes sense to start with the Gaussian model because it's simple, because it looks reasonably good for our set. So it makes sense to start with a simple model that I believe, looking at my data, to be a good fit for our samples. Of course, other models may be better. I will need to try reasonably good things, reasonably complex models, and then decide which one to use. When should I stop? Well, we are engineers, so we have tasks to solve with constraints on cost, time, and so on. So I may start with a simple model. I may try a more complex model if I decided it's worth the additional cost or not. But all these decisions are decisions that will depend on the task and the results that I have. Let's, for the moment, do the first step, decide that for the moment we try to see how good a Gaussian model would be. We try to fit Gaussian densities to describe the class conditional densities. What are the class conditional densities? Essentially, they are the density that describe the features of each class. So the distribution of the features of each class taken as if they were the only ones. Intuition, the idea here is, if we want to build a class conditional model, we can try to fit a Gaussian density to the sample of each class. We already have seen that we can use Gaussian densities to describe samples. We have seen how to fit a Gaussian density to a data set. So, intuition, we can take the female samples and fit a Gaussian to the female samples. We can take the male samples and fit a Gaussian to the male samples. And then decide that this will give us what? A Gaussian distribution for the males, for the females, and the Gaussian distribution for the males, and we will use these two densities as the class conditional density. So this will be the density if I put X, so this will be the conditional density given, so given female here, and this is the density given male. And from the histograms, I can see that there is a reasonable match between the histogram and the density. So probably the Gaussian assumption is fairly good for this task. Now, if I do this, I can compute the maximum likelihood solution as we have seen before, the break. I would end up with the mean of the male class, the mean of the female class, empirical variance of the male, and empirical variance of the female. These are the four parameters that I need to estimate. 2 for the male class and 2 for the female class, so male and female. Now, once I've computed this, I can compute my class conditional density. My suspect was 174. I can compute the density for the 174 suspect. I take the Gaussian density for the male, I plug here the values that I computed, and I plug for X 174. This is the likelihood of the 174 centimeter tall person given that it comes from the male class. It's what? It's the height on this curve of 174. So it's this value here. I do the same for the female, which will be somewhere here, and I get maybe a bit lower here, and I get 0.1, 0.01, etc. What does it mean? It means that there is roughly 5 times the chance that I observe 174 person tall in the male class with respect to the female class. Notice that this is not the answer. This does not tell us that the probability of male is 5 times the probability of female. It tells us that the probability that I observe somebody with 174 centimeter tall in the male class is 5 times the probability, I should say likelihood, that I observe somebody who has 74 centimeters tall in the female class. So it's the ratio between these two values. How do I obtain the answer to my problem? I need to combine it with the prior class probability. Combining with the prior class probability of male and female, I can obtain the class posterior probability. This is what I want to compute. Why? Well, what is this simulating? Well, let's see with the female-male example. So these are the class conditional densities, okay? Male and female. Now, this tells us the class conditional probability. So the probability of seeing 175 in the male class with respect to the probability of seeing 175 in the female class. But that is not all the story. What is that I want to compute? What is the probability that I have a male or a female given that is 174 centimeters tall? That does not depend only on the ratio of these two values, but also on how many males I have in my population. Imagine that. Remember that these are densities, class conditional densities. But what I want to compute is the joint probability of male and 174, female and 174. If I have, for example, a place where the country has 90% of people who are female, then if I were to plot the frequency in the whole population of 174 people tall, I would scale this quantity by prior female 0.9, so it would look something like this, and the amount of people who are male and with some height would be this density scale by 171. This is the joint probability of some height and male class, while this is the joint probability of female and the X as height. Joint probability tells us what is the probability that is both X, so 174 in our case, and male. Since males are much less than the females in this example, I end up that there are more people who are 174 and female than people who are 174 male. Again, the density tells us that it's more likely that I see 174 in a male rather than in a female class. But doesn't tell us how likely it is that I see somebody who is 74 and male, or 174 and female. That depends on how many females and how many males I have. How many females I have that were 174? I have this quantity times the fraction of females in my population. How many males I have that are 174? The probability that one is male and 174. So the prior probability scales these quantities. Essentially, if you see it in terms of histograms, you have that these are histograms normalized so that the two populations are considered equal. So there are one female to one male, because the area below the histogram is the same. But if I were to normalize the histogram so that they reflect the fraction of the population of male and females, if I have 90% females, I would have, this would be the histogram of females, and this would be the histogram of males. Normalized in a way that the female population is 0.9 female for each 0.1 male. So prior probability scaled by the prior probability. Which means that if I have somebody who is 175 tall, there is more chance to see a female that is 174 tall than a male who is 174 tall. Why? Because once I take into account the prior probability, which I can see as I rescale the histogram so that the area below the curve does not represent a unit of the same population, but is proportional to the probability that the prior probability of the sample belonging to that class. So the area below here is proportional to the females in my population, and the area below here is proportional to the males in my population. I will see that there is higher chance to have somebody who is female and 174 tall than male and 174 tall, because there is a 9-to-1 ratio of female to males. Numerically, you have it in this example. If the two classes have the same prior probability, so the class conditional density gets scaled by the same amount, the ratio of the two populations are the same, then the prior probabilities are the same, and the class conditional ratio is exactly the class posterior probability. But if my classes are unbalanced, once I plug in my prior probabilities, they may give us a different answer with what I got by looking just at the ratio between class conditions. So the class conditional ratio tells me that the probability of seeing 175 in the main class divided the probability of seeing, it's not probabilities, again, I use the word probability, but it's likelihood. I use probability because it's easier probably to understand. But it's about 4.5, but then the prior probability of male with respect to female is 1/9. So when I combine these two, this suggests that I should go towards the male class. But the prior probability tells me that I have to pay attention because there is a much higher chance to observe female. So the combined effect, finding somebody who is both 174 and female, there are twice the amount of people who are 174 and female with respect to the people who are 174 and male, which tells us that the class posterior probability ratio is 1:2. The class posterior probability for male given 174, in this case, is I don't have the number, but is 1/2 the class probability for being female. And notice that this means that I will label the sample as female in this case. With uniform prior probability, I would have labeled the sample as male. So the model will give me this ratio, tell me the ratio between the class condition is 4.5, and then depending on the class prior probability, I will say that this 4.5 leads to saying that the point is male or to female, depending on the value of the class prior probability. So the model, the Gaussian density model, gives me a way to estimate class conditional densities. The class conditional densities gives me a strength towards one hypothesis. The strength tells me that I'm geared towards the hypothesis that is male. So I need a stronger counter evidence from the prior probability to change my opinion. But the final answer will not depend on the model alone, but also on the application prior probability. I change the application prior, I will end up with a different solution that we will see is optimal for the application that I'm considering. So we will show that the prior that I use there leads me to optimal solutions when it's combined with the output of my model. So the generative model builds a model for class conditional densities. So the distribution of the samples inside each class, the distribution of the sample inside each class tells me whether a given value is more likely in one class or in the other. But then I need to multiply this value by the prior probability to know whether the combination observation in class is higher for one class with respect to the other class. And that will lead me to find the joint probability that you can see gives me the correct answer already. Notice that here I didn't compute the marginal. I just need the joint to reach my conclusion, because the marginal is, we said before, is just a constant that is equal for all classes. So it will not affect what is the maximum. And indeed, if you see here, I didn't compute the class posterior. I just worked with their ratio. Working with their ratio allowed me to simply avoid computing this term here. So we didn't even need to compute that term in any case. F175 in the original slide. The marginal for the height, well, 174 it was. Okay, questions? Okay. So this is the whole idea. Now we gave it in an intuitive way. We said, let's fit one Gaussian density to the sample of each class. And we did it independently. We computed a mean for the male and a mean for the female class. Now, we will try to formalize all this in a way that leads us, of course, to the same solution as the intuition for the simple task, but also tell us how to do when things become more complex. So it gives us a framework that, again, as for the maximum likelihood for the Bernoulli, it will lead to solutions that are reasonably simple, exactly the solution that we saw for the problem that we analyzed now, but gives us a way to approach, to look for solutions where things become more complex. So will give us a framework, and we will see that, again, the framework will be based on maximum likelihood, maximization of a likelihood that will be defined in a suitable way for the task, for the multiclass task. So now we extend our model to feature vectors that may be not just scalar values, but vectors. For example, you can extend the previous task by saying, okay, I collect the height and the weight. So now I have a random vector, not a scalar anymore. So I need to model my samples in 2 dimensions. I will have samples for the male class and samples for the female class. And then my test sample that I want to classify. In this case, my feature vectors are 2-dimensional. We also consider a general case where we have k classes. So rather than male, female, we have something else. So 3 classes. 3-class problem. And we need to put a label for all those classes. Then we will see that for binary problems, there are some specific things that we can use. For multiclass, we will see that whatever we define for multiclass also applies for binary, but for binary, we'll be able to do something a bit better. Now, again, we assume that the samples of each class can be modeled by a Gaussian density. So for each class, we assume that we can model the samples of the class as being generated by a Gaussian density. So in 2 dimensions, it's difficult to draw them, but I will have a 2D density for the samples of one class. And then I will have another density for the samples of the other class, and so on. And the samples of each class will be modeled by a Gaussian density. But I prefer to draw it in this way because the 3D drawings are not that good. So I will use a Gaussian density with a mean and a covariance matrix this time to model the samples of each class. Notice that I have a covariance matrix which may not necessarily be identity, so it may have different axes. So it may model things like this class or a class like this, and so on. We assume that each class for the moment has its own mean, is described by its own mean and its own covariance matrix. So the covariance matrix is different for the samples of each class. Now, if, again, frequent this approach, if we knew this, then our predicted distribution for the test sample and the class, so the one that we need to compute the class posterior probability, remember to compute the class posterior probability, we need to compute for all classes the probability that I have class XC given the sample that I observe is XT for the test point. And for this, I need to compute the class conditional probabilities for the samples given all possible class labels. So for each of these classes, I will have my test point here, and I will compute the likelihood using the density of the yellow class. So here I will have a value for the likelihood of the yellow. The same for the green, for the red, and for the blue point. If we knew the parameters of the Gaussian of each class, we could compute all these, and then we could compute class posterior probabilities. In one dimension, it would be like I have three classes. I have the model parameters for each class. I have my test point. I can compute the class condition on the yellow, on the blue, and on the red class. Then combine this with the prior probabilities and obtain class posterior probabilities as we did in the previous example. Problem is, we don't know the parameters of these densities. As before, we said we want to model the densities, but we don't know what is the mean of the density for the female class, what is the mean of the blue. Before we said, let's independently fit a Gaussian density to each class. So what implicitly we said, let's divide the samples into classes. For each class, we solve a maximum likelihood problem, which consists in finding the parameters of the Gaussian density that best fit the samples of that class in a maximum likelihood sense, and then use those parameters as the solution to our classification estimation problem. So implicitly what we did was exactly this. We said we don't know the model parameters, but we try to estimate them from the data. Before we said by independent maximum likelihood fitting of the samples of each class. Well, we show that this, under the assumption of this model, is the correct thing to do. So we have our training set, and what we want to do is use the training set to learn the model parameters. So for example, we have height and weight for the male and female class. We want to fit a model that says that each of these is described by a Gaussian. So we need to find the mean and the covariance matrix of the male class, and we need to find the mean and the covariance matrix of the female class. Okay? It's the same as before, just multidimensional. Assumptions. The assumptions that we do are those that we implicitly did before. As when we were doing density estimation, we assumed that given model parameters, the observations are independent and identically distributed. So once I know the model parameter, knowing the values of the dataset is irrelevant to say anything about the future samples. The model parameter condenses all the information that I have on the problem. So given the model parameter, the samples are independent. And we also assume that they are identically distributed. Given the model parameter, they all follow the same joint distribution. So if I take a pair feature vector and class label for one sample, that will follow the same distribution as the other samples, that will follow the same distribution of the one that I need to classify. So all samples can be assumed to be drawn from the same distribution. And let's plug our model in. The class conditional distributions are Gaussian distributions with mean and covariance matrix that depend on the class label. So for each class, the distribution of the samples, given that the class is small c, will be small c. So for example, the distribution of a feature vector of height 170 and weight 75 given male will be computed with a Gaussian density computed at the value 170 and 75 using the mean mu m that I will have estimated for the male class and the mean and the covariance sigma m that I will use for the covariance of the male class. The set of all parameters, we call it theta just for simplicity. What we want is to find an estimate of theta. Once we have the estimate, we'll use the estimate as class conditional to compute the class conditional density. So we will use the estimate to compute, given a test sample, to compute the joint probability of the test sample and the class for our observed sample that we want to classify. For the joint probability, again, we will use the class conditional probability times the prior. This class conditional probability will be computed using the Gaussian density with the estimated values for the model parameters. So we will take our training set, compute the male and female optimal parameters, and then if we want to classify this guy will be, we will compute class conditional using the male class, and then we will compute class conditional of the same feature vector given female using the density for the female class that we just estimated. And we will see that again in a moment. The first step for this is to find the solution. So for the first step, before we can use the parameters that we estimated, is to find what is the value that we want to use for this parameter. So given the dataset, the first step is to estimate the mean and the covariance of the classes of my dataset. Now again, we follow a maximum likelihood approach. We start writing the likelihood for our parameters for our dataset. What is the likelihood? The likelihood is defined how? As the joint density of all the observed values of our dataset. Which means in this case, all the feature vectors and corresponding class labels of the observed dataset. So for example, in my dataset, I may have that I have labeled this as male, then I have one other male, then I have female, and so on. Each of these pairs will be a x1, c1, small x1, small c1, x2, small c2, x3, c3. They will be the values that I observed in my dataset. So the likelihood is the joint density for all the random variable that describes my dataset computed at those values. So if this were discrete, it would be the probability of all the observed values. It's not, again, a probability because these are densities, so it's a likelihood function. It's the density computed at the observed values. Assumptions. IID given model parameters, which means that if we know the model parameter, then this joint density can be factorized over the single component. It can be rewritten as a product over samples of what? Of the joint density of a sample and the corresponding class label. So for all these samples, here I would have the joint density of 170, 85 male times 180, 75 and female times whatever. And since they are all identically distributed, I can drop the index I because the density is the same for all the samples. We have a common density for all of them. So the function that describes the density does not depend on I. The only thing that depends on I is the point at which I compute the density. Now we need to introduce our model. Before we can do that, we need to rewrite this in a way that highlights the dependency on the model parameters. Here we wrote it as just dependent on theta, but let's see how this depends on theta. Well, the joint density, we have said, generative model, we factorize it as a class conditional likelihood that depends on the parameters times a prior probability, this is small c. you want here, there should be a big C or just big C without the I because we dropped the I altogether. So it's the class conditional density times the prior probability. The class conditional density is the Gaussian density. So for example, for our previous example, which had 170, 85 male, then we had 180, 75 male, and then 170, 70 female. These were our samples. My likelihood would look what? Would be a Gaussian computed in 170, 85 using the male parameters times a Gaussian in 180, 75 using again the male parameters times a Gaussian 170, 70 using the female parameters. And then we said times the prior probability of male, but these do not depend on the parameters, so we will see that these values actually will not influence our estimate because they do not depend on theta. For a moment, let's just write. This would be the likelihood for this data set, okay? It's a function of the 4 parameters, mean and covariance matrix of the 2 classes. All the rest are numbers that are known. And whether I should use M or F here depends on the label of the corresponding class. Again, let's switch to logarithm because it's easier to manipulate this expression in log domain. In log domain, our product becomes a sum over samples. Of what? Of logarithm of this expression. This is a product, so I can split this product into log of the normal density plus log of the prior probability, okay, for each term. Then I have a sum over samples. I group this sum, the terms that depend on the density, and I group together the terms that depend on the prior probability, and I can write my expression in this way. For each sample, I have the density computed at the sample using the parameters of the corresponding class. So for example, for the first sample, again, 170, 85, I would use mu m and sigma m. For the second also. And for the third, I will use 170, 70, female and female. Now, I observe that these terms here do not depend on the parameter theta. My goal will be maximizing with respect to theta, so I don't care what these values are, they are an additive constant to my log likelihood. So I can just ignore what the value is. Whatever is the prior probability, it will not influence the solution to my maximum likelihood approach. Maximizing this with respect to theta will not depend on the value that I give to P. Again, these priors do not depend on theta, so they are just an additive constant with respect to our function. So now we have a log likelihood, one more step, that corresponds to a summation over samples. And this one, we throw it away and we collect it into a constant. Now this log likelihood, let's rewrite it in a easier to manipulate way. How? Well, let's imagine that I have sample x1 from class male, sample x2 from male, sample x3 from female. Then let's add another from female and so on, like this. What would be the log likelihood in this case? Would be log normal of x1 given male plus log normal x2 given the male plus the same thing given the female. So let's put x3, let's put log, plus logarithm of the same thing of x4, in this case male, plus logarithm of x5 given the parameter of the female, okay? This would be the sum that you have in this expression. Now let's arrange these terms as to put before all the male samples and then afterwards all the female. So we group them in which way? We have x1 male, we rearrange the samples in this order. x1 male, x2 male, x4 male, and then x3 female, x5 female. So we can say that it's a sum over the sample 1, 2, and 4 of what? It's a sum over. It's the sum of the log density of x1 given mu m, sigma m, and then x2, and then x4, plus the same summation, but this time of x3 given mu f, sigma f, and here I have x5 given mu f and sigma f. So I can express it as a sum over classes of what? The sum of the samples that belong to that class of the logarithm of the Gaussian density, where this mu now do not depend on Ci anymore, because all Ci's in this inner sum are equal to the same value C. So this allows me to drop the fact that before I had a dependency of the index of the parameters on the samples. If I rewrite it in this way, I group together all the samples that belong to the same class. So now I can parameterize these parameters directly by the class C that I'm considering is the inner summation. So I can drop the dependency on the parameters on the index of the sample, because I moved the indexing essentially in this part of the summation outside. So I can write it as a sum over all classes of what? For each class, I have a sum of the samples of that class of the logarithm of the Gaussian density computed with the parameters of that class. But this is what? This is exactly the log likelihood of a Gaussian model for the samples of that class. So if I extract from my dataset the samples of class C, and I write the Gaussian density, the likelihood for those samples when the Gaussian model is given, parameters are given by mu C and sigma C, I will get exactly this expression. This is what we got when we did density estimation before the break. This is the log likelihood for the samples of class C under a Gaussian model where the parameters of class C appear inside. And notice that the summation of classes here each time considers a different class, and the parameters inside each sum are independent. What does it mean? It means that writing the summation in this way, I get that I can decompose my log likelihood into a sum over classes of likelihoods. Each of these likelihoods depends on a different set of parameters. Each time I change the index of the sum, I change the parameters that I have inside this function L, which means that the max of L over theta is obtained by independently maximizing each of these terms with respect to mu C and sigma C. So I can independently maximize each term in this summation. The overall sum will be the maximum that I can get for the likelihood. But this is nothing else than the log likelihood of a model, Gaussian model, for the samples of the class when the parameters are mu C and sigma C. So we already know how to maximize this if this were one-dimensional. If this were one-dimensional, the solution would be the mean of the dataset and the variance of the dataset, in this case, of the samples of that class, which is the dataset over which I'm computing my likelihood in this context. So we can, when we assume maximum likelihood solution where the model parameters are independent for each class, so each class has its own set of parameters, indeed the maximum likelihood solution for the whole dataset corresponds to the maximum likelihood fitting to independently finding the maximum likelihood fitting of each density to the sample of the corresponding class. So the maximum likelihood solution for the whole problem is obtained by finding the maximum likelihood solution for each class independently. So what we did before, we said let's fit a Gaussian density to the male and let's fit a Gaussian density to the female independently is indeed correct if the model parameters are assumed to be independent, so different for each class. We see an example where this does not hold anymore, and in that case, we cannot independently fit the densities anymore. But if we assume that each class is characterized by a different set of parameters, then the maximum likely solution can be obtained by independently fitting by maximum likelihood a density to the samples of each class. We already know how to do it for the one-dimensional case. It remains to see how we do it for the multi-dimensional multivariate samples. So what remains now, and I will start, let's see where we get, and then I will finish tomorrow. We now need to find the maximum likelihood fit of a multivariate Gaussian model to a given set of samples. In our problem, this will be the samples of a given class. And then we will repeat the process a number of times equal to the number of classes. So we will fit one Gaussian model to each class. How do we find the maximum likely solution for the multiclass? Well, let's start writing the log density. It's not much different from before. We need to write the log density and then find the log likelihood and then maximize it with respect to the model parameter. Now let's, for simplicity, drop the index. So we go back to a density estimation problem. We have a set of samples which are characterized by a Gaussian density with mean mu and covariance sigma, and then we want to find the maximum likelihood fit. Then we will repeat this for each class, and that, when we do a classification task, will lead us to find mu1 sigma 1, mu2 sigma 2 for the different classes, and so on. So for the binary problem, mu male, sigma female, and the same for the mu male, sigma male, and mu male, sigma female. But let's now consider that we are doing it for a single class. Or in general, we are fitting a Gaussian density to a given data set. This is the Gaussian density, which we can write the logarithm of the Gaussian density, which we can write as a function of lambda. Now, we already start observing something that will look interesting, that was not that evident when we were working with the density itself, but it is more evident when we work with the logarithm of the density. The logarithm of the density has this expression, which we can write in terms of precision in this way. Now, if I have to look at this as a function of x, which kind of functions do I have here? Let's say that I tell you, I solve this equal to k as a function of x. What would it will look like? What kind of shapes I can expect? What is it? So depending on the value of k that I don't know, but what kind of shapes I can expect provided that I have a solution for the equation? I have ellipses that are controlled by lambda. So for different values of k, I will get different ellipses. And the ellipses axes, we said, are related to the eigenvectors of lambda, which happens to be the eigenvectors of sigma. So the eigenvectors of the covariance matrix control the shape of the density. So we can see that as a function of x, this is a quadratic, what is called a quadratic form. It's x transpose something x plus something that depends on x plus some constant. Actually, if we develop this, it will be x transpose lambda x times something that we don't care plus, so it will be something plus something that depends on x plus some constant. So It will be a quadratic form in X. And this will be useful later, so remember this. Now, let's take this expression and write our log likelihood. What is the log likelihood for our dataset? It's a sum over samples of the logarithm of the Gaussian density when the parameters are mu and sigma. This is the definition of log likelihood. This is the definition. The definition is, well, this comes from the definition and assuming independence and identically distributed random variables and so on. Is the value of the log density computed at the samples, summed over all samples, when the model parameters are mu and sigma. So we take this expression and we put it in place of this summation. We have a summation over samples. If I sum this over samples, I get a summation over samples of this expression. If I have this over samples, this will be xi. Now, as before, I have a sum of constant terms that I don't care. Then I have a sum of 1/2 log determinant of lambda. This does not depend on x. So when I sum this, how much do I get? How much is this? N times what's inside the sum. And then I have a sum of these terms. This is what you have in the next slide. Okay, here we get again the class C. So here actually we're in the slides, we are solving directly for a classification problem. So we are considering this is the solution for class C. But this can be generalized to any problem where mu C and lambda C are the parameters of the Gaussian that we want to fit to some data. So we have a constant, then we have number of samples, logarithm determinant of the precision, minus 1/2 the sum of the sample over the samples of this expression. Now the sum of this expression over the samples, we need to do a couple of tricks to manipulate it, to bring it in a way that we can work with. Actually, we will not see why these are useful. Well, we'll not see why these are useful for the derivatives, but they are. But it's interesting because to see how we can write it, because they show, they tell us something on the data. Remember that this is a scalar. So a scalar can be interpreted as a one-dimensional matrix, and the one-dimensional matrix is equal to its own trace. So whatever is here, I can write as a trace of this. So I can write the trace, sum of a trace. A trace is itself a sum, so I can exchange the order of summation. So I can write everything as a sum of, a trace of the sum over samples of xi minus mu transpose lambda xi minus mu. And then, actually I would do the opposite, in the opposite order, but the trace being circular, I can move this last term, first term at the end, and write it in this way. This is independent on I, so I can bring it outside. Short, I can rewrite it in this way, or even better, when I split the square, how you see at the bottom of the slide. Why is this useful? Because this shows us how the likelihood depends on the data. The likelihood function depends on the data through the number of samples, the sum of the values of the samples, and the sum of the xi transpose values. We call these zero-order statistics, first-order statistics, and second-order statistics. These are a function of the data set. And once I computed these statistics, the likelihood function depends on the data only through these statistics. These are also called sufficient statistics because they collect all the information that is relevant for the estimation of my parameters. What does it mean? It means that two datasets which have different samples, but for which these values are equal, will be, from the point of view of my model, exactly the same thing. They will lead to the same model. So the sufficient statistics are a summary of all the information that my model can extract on the dataset. My likelihood function depends on the dataset through the statistics. So the statistics collect all the information that my model can gather from the dataset. And in this case, the statistics are these quantities. Whatever are the samples, if I have two datasets with the same sufficient statistics, they will lead me to the same inference model. Then we can find the maximum likely solution by solving. In this case, we need to take gradients with respect to the model parameters and put them equal to 0. So we need to differentiate with respect to all the elements of lambda. So lambda c will be a matrix. Let's write lambda 1, 1, lambda 1, 2, etc. So we take the partial derivatives of the likelihood with respect to all the elements of lambda c. The same for mu. This will give me a large set of equations, depending on the number of samples that I have. And then I put this equal to 0 and solve for lambda and mu. Solving for mu is easy, gives me this solution. It should not be surprising. The maximum likely solution is the empirical dataset mean. In this case, if we are estimating this for a class, it's the mean of the samples of that class. And for the covariance, again, we should impose some constraint because the covariance matrices should be definite, positive, and symmetric. We solve the problem in the unconstrained way. We will see that the solution respects the constraints, so we can avoid explicitly asking for the constraint to be met because our solution will still meet them, provided that the empirical covariance matrix of the dataset is positive, definite. That will be the maximum likely solution for our covariance. So the maximum likely solution also in the multivariate case will be the mean of the samples that I'm fitting and the empirical covariance matrix that we already know how to compute for the same samples. If I'm fitting this to the samples of a class, it will be the mean of the samples of that class and the empirical covariance matrix of the sample of that class. Okay, I think that's enough. Tomorrow, I call you that it's virtual because we don't have the class. We'll have first laboratory and then the lecture and then the other two laboratories.